Morning, everyone. So I'm presenting this work on behalf of my student. So he cannot attend here also because of the visa situation. So today I'm going to share of our research, LLM-PCPP, a novel robot prioritized coverage path planning approach for complex environments. So let's get started. So autonomous robots are increasingly used in complex environments. Like construction sites and warehouse. However, traditional coverage path planning, they consider the entire environment equally. As you can see on the right-hand side, they try to cover the entire environment, but they will do is to visit every single places in the environment, which is more inefficient in that situation. So our goal is to develop a smarter, more efficient approach that focuses on prioritized coverage path planning. So it's targeting the most important areas while minimizing the computational loads of the algorithm. Okay. So our approach is called large language model LLM-based prioritized coverage path planning LLM-PCPP. So we will use this for efficient mobile robot path planning in a complex environment. So a few things we want to identify. First is the point of interest. So we use LLM to identify point of interest from the semantic grid map in order to let the robot know which area should visit more often in order to get more cover of that. And so once we have the point of interest, we use the robot path planning to optimizing using a hybrid LLM A and also a traveling salesman problem TSP strategy. Both of them to use them in more efficient and computational and in more efficient way. So here's our system. So here's our system workflow flowchart. So we start with the environment. We get the sensor data from multimodal data, integrating either RGB or light and LiDAR data, and then we convert to the perception data. We from the environment to get more semantic grid map. So we will know object proximity. We have an object like a concrete block. We can get this in more in a description way. We have object concrete block. What's the distance? What's the angle? And in a different area, we also want to identify some point of interest. But once we have this semantic grid map with the description, we will pass this semantic grid map into the LLM in order to get some extract the point of interest. So we use the prompt engineering process to let the human instruct the LLM how to get the point of interest. Then they will extract the point of interest like this, and then we will use our proposed PCPP method to plan the path. And our research in this paper, we focus on the right-hand side part. We assume we can already get the semantic grid map based on our prior research, converting from the environment to the semantic grid map. So here's some detailed methodology. You can see from here, we have the semantic grid map construction from the several drone videos from the top views, converting from a 2D grid map with the binary navigability from these photos. Convert from this to there. And each grid cell contains some spatial and semantic information to let the LLM know whether what is in that area and whether they are navigable or not. And once we have the semantic grid map, we feed the grid map into the LLM. So LLM will analyze the semantic grid map description, and they will output the task relevant point of interest, POI. So here are some examples. The red dots are the point of interest extracted by the LLM agent. So you can see we have several hazardous areas equipment areas and also storage areas, if that is a construction site or warehouse environment. So with all this, the robot will be able to know which area are the top priority environment they should cover. They should visit to cover those areas. Then we applied one of the hybrid path planning algorithm is called LLM A. So the LLM A, they combine the LLM with A process. So the traditional A process, one of the issues with the A is they need to explore the environment. So as you can see here, if our mobile robot they have the limit storage, memory storage, they will have some difficulty to cover the entire area. So we use the LLM A method to introduce some intermediate waypoints. So in this case, for example, the robot wants to navigate to here. Then we ask the LLM to find some intermediate point based on this environment. So they identify this point and this point. Then the A will start to do the process without exploring the entire area because they already know there are several intermediate points they can visit first to reduce some computational storage requirement. And another thing we use is the traveling salesman problem solver. Once we have all the point of interest, the robot will have to determine how to visit every point. So in order to cover the environment. So that is basically a traveling salesman problem. So we can directly use all our tools for solving this traveling salesman problem. Every point of interest, the robot will only visit one time. Then once they determine the sequence of the visiting, we can apply the LLM A process to determine the path to visit to those point of interest. Okay. So to evaluate our system, we create 3 scenarios. First is a complex outdoor construction site. The second is a simple outdoor construction site. So here is the more complex environment, and here is the more simple environment. And we also created an indoor warehouse scenario in the virtual simulator. And we evaluate our method by using the path length, the result path length, the operation, basically the computational steps, how many steps they need to determine the coverage path, and also memory storage, how much memory storage we used. But as you can see here, we compare the LLM-PCPP with the traditional A baseline method. The result you can see from here, all the path length are increased because the LLM A is not the optimal solution. The A is the optimal, they will find the optimal path, the shortest path. But LLM A they first determine the intermediate waypoint. So that means in some case, the path length will increase, as you can see here. But in all the other scenario, the operation of the computational steps and memory usage all decrease significantly because they don't need additional memory usage in order to explore, because we already provide some intermediate point for the A algorithm. So I'm showing some of the result for the path planning. On the left hand side is the traditional A, right hand side is our LLM-PCPP method. You can see they have some intermediate point here that's caused the increase of the path length, and also some of them are here. You can see compared to the traditional A, they will only find the shortest path between each point. Here's a simple outdoor construction site situation, and indoor warehouse scenario. So in conclusion, we developed an LLM-based prioritized coverage path planning algorithm, LLM-PCPP approach for mobile robot navigation in complex environments. So we leverage LLM to identify the context-rich point of interest and also LLM A and traveling salesman problem to determine the efficient path between each POIs. We successfully reduced the computational steps between around 40% and memory usage around 35%. But we have also caused some path length increase about 20%. So that's some drawback for our system. So I would like to take any question. Thank you.